Okay. Let's go to lesson 3, gravity. I was going to ask questions, but I didn't give you very much time to work on the worksheet, so maybe I'll just ask questions for both tomorrow, and then we'll go over questions. I don't know how much of this I want to do. Actually, yeah, I'll just do this page, and then we'll see how much we do tomorrow. Yeah, okay. Let's just deal with this lesson today because it's a pretty short unit, or pretty short lesson. So gravity, and you're probably thinking, we've done gravitation, this is kind of stupid, but we really haven't. So right now, our formula we have is Fg equals m times g. Okay, that's what we've been told is gravity. It's a little bit different than that. So Newton discovered that gravity attracts any two objects depending on their masses and their distance apart. Okay, so even the value of g changes depending on where you are on Earth. Okay, so the Earth is it's a terrible drawing. The Earth is elongated in the middle, and I'm exaggerating it a lot. And it's so if you're standing on the equator, the distance you are from the center of the Earth is different than if you are in Vancouver. Okay, you're actually closer to the center of the Earth than on the equator. So the value of g is stronger where we are than it is on the equator. It's actually less than 9.8. And if you were to climb a mountain, the value of g gets lower and lower. Okay, so it depends on how far you are from the center of the Earth, because that's what's pulling you towards Earth. So Fg is proportional to the two masses. So this alpha symbol here means proportional. So it means that if one mass goes up, Fg is going to go up, or if both masses go up, then Fg will go up. So it's directly proportional to m1 times m2, so the product of their masses. And it's inversely proportional to the square of the distance between their centers. So that means it's an inverse is 1 over, so 1 over, and then we're going to call it r squared. And r is the distance between the centers of both masses. Okay, and this is what Newton discovered. So putting this all into a formula, you get the formula Fg equals big G m1 m2 over r squared. Now, this big G here we have is nu, okay, and G is a universal gravitational constant. And the value of it is 6.67 times 10 to the negative 11 newtons. What is it? Newton meters squared per kilogram squared, I believe. I think that's what it is. Meters squared divided by meter squared. Kilograms. Yeah, I think that's what it is. It's on your formula sheet. So, and this is just, I don't know who figured out this constant, but it's just it works. That's how we figure it out. So, I'll show you. Actually, maybe I'll apply this to Earth first. Okay, so on Earth, so if we want to find the force of gravity between like based off of our mg, so let's say we have a 10 kilogram object. Okay, the force of gravity dependent on g on the surface of the Earth with the average value of 9.8 would be 98 newtons. Okay, well, if I apply that here and to the big formula, then I have big G, 6.67 times 10 to the negative 11, times the mass of our object, 10, times the mass of the Earth, 5.98, times 10 to the 24 kilograms. I don't remember what it is. I think that's what it is. And then divided by the radius. The radius, the average radius of the Earth is 6.38 times 10 to the, oh crap, 6. I think it's 6 squared. Let me check the formula sheet for a sec. It's been a while since I've done this unit. Oh man. Okay, so on the second page should be all your constants. Okay, here we go. So the mass of the Earth is 5.98 times 10 to the 24. Okay, good. And the radius of the Earth is 6.38 times 10 to the 6. Perfect. Okay, I got it. So if we do this, 6.67 times 10 to the negative 11 times 10 times 5.98 times 10 to the 24, and then divide that by 6.38 times 10 to the 6 squared, you get 98 newtons. Okay, and that's the exact same. So the value of G is coming from this formula. Okay, it's not anything new. It's just that's where it's coming from. Okay, so it's actually a bigger formula than what we've been taught, but and some of you have probably seen this before. It's often taught in Physics 11 as well. So okay, so calculate the force of gravity between two 75 kilogram students if their centers of mass are 0.95 meters apart, so pretty much a meter apart. So Fg will equal 6.67 times 10 to the negative 11 times the first mass, 75, times the second mass, 75, they're both 75 kilograms, divided by the radius, so the distance between their centers, so 0.95 squared. Okay, so 6.67 times 10 to the negative 11 times 75 squared, because we're doing it twice, divided by 0.95 squared, and you get Fg is equal to 4.2 times 10 to the negative 7 newtons. Okay, now that's a very, very small value. Okay, gravity is actually a very weak force. Okay, it's not strong at all. Let me go back to the chat. Oh, I don't know what that was. Okay, so it's a very, very weak force, and the only reason it exists like in nature is because objects are really big. So the reason we can feel it on Earth is because the Earth is really big, and therefore we experience its gravity. Give me one sec. And so it's a really, really weak force. However, if you're ever in a relationship or wanting to be in a relationship and you go up to somebody and say, hey, you want to go on a date or something like that, and they say, no, I'm not attracted to you, you can prove that they actually are attracted to you based off of gravity. So, but you have to ask them their mass, and that's probably offensive, so it probably won't work. But again, nerd alert, you can do that now. Okay, so that's the force of gravity exists between any two objects, and obviously if we get much smaller, like on a subatomic level, it's way smaller, right? So like there's barely any gravity existing between atoms, but in space where there is no other force, then it's like there's no resistance causing them not to move, then like atoms come together based off of gravity and electrostatics, which is the next unit. So Okay, you'll often see problems that ask something like this. So a satellite weighs 9,000 newtons on the Earth's surface. How much does it weigh if its mass is tripled and its orbital radius is doubled? So these types of questions where it's saying things will double, triple, all that stuff, what you need to do is you need to say, okay, the weight of the object, and physics is going to get me girl someday, right? Before we even start this, let's again clarify the difference between mass and weight. Okay, every time somebody says, "Hey, how much do you weigh?" you always give them pounds. Okay, but that's technically wrong. Mass is kilograms. Okay, it's how much stuff you're made of, and weight is newtons. Okay, typically this refers to Fn. Okay, this is called apparent weight. This is what you feel. Apparent weight, I think I spelled that wrong, whatever. And then Fg is your true weight. It's what gravity, what the Earth is doing, pulling you down, true weight. Now you can be weightless if your Fn is 0. And so Fn is like if you go on a roller coaster, your Fn changes, and whenever its G is not 9.8 or if you're accelerating something other than 9.8, you'll feel that. So your Fn changes. Okay. So if the satellite weighs, and by weight we mean Fg in this case, 9,000 newtons on the Earth's surface. So that means that Fg equals G m1 m2 over r squared. So it weighs 9,000 on the Earth's surface. So 9,000, whoops, 1,000, not 100, equals G m1 m2 over r squared. How much does it weigh if its mass is tripled and the orbital radius is doubled? So what we're going to do is we're going to take this relationship and we're going to say, okay, what would it be if G stays the same, the mass of the Earth stays the same? We're going to triple its mass, 3m, and double its orbital radius, so 2r squared. Okay, and then you can kind of work this out mathematically. Fg will equal G. Actually, we'll move that 3 over. So we'll go 3G m1 m2 over, and then this is going to be 4r squared. Well, if 9,000 equals this part, that's this part right here. And so the new Fg will be 3/4 times 9,000. Okay, because it's just a relationship between the two. And so 9,000 times 0.75 is 6,750 newtons. Okay, so the new weight, you don't have to do it over again. You can just use a relationship between how the two change. Okay. Again, if there's any questions, please ask or stop me if you don't know what I'm talking about. Satellites, that's the next big thing we're going to talk about, is satellites around Earth. So a satellite of the Earth, satellite just means orbit, such as the moon, is constantly falling. Okay, so the only difference is it's not falling down, it's falling sideways. So if you think about the Earth, here's the moon. Again, the Fg is going that way, so technically it's in free fall, but the moon is going this way. Okay, so it's falling sideways, sort of. I know that doesn't really make sense, but so it's constantly falling, it's constantly in free fall would be a better term, but it does not fall towards the Earth, rather it falls around the Earth. We talked about this morning. Just as if you were in an elevator that was falling towards the Earth, you would feel weightless. If you were on an artificial satellite falling around the Earth, you would also feel weightless. Now, if you think about consider the moon, I don't know what I'm supposed to do there. I can't remember what that blank is there for. I think I drew it right there. We're fine like that. Okay. So if we apply this to satellites, and in this case, the FC will equal FG, okay, of the moon and of the moon and the Earth. So if we apply this, like the FC acting on the moon, so this will be like mass times mass of the moon. And then if we wanted to know like the speed or something like that, we'd go V squared over R equals G M Earth times M moon over R squared. The mass of the moon doesn't actually matter. And then you can start solving things like that. So in terms of satellites, the important part is that the FC is equal to the FG. Okay, so let's look at an Earth satellite. So like the satellite that gives us cell reception or whatever. 45 kilogram Earth satellite has an orbital radius. So orbital radius, this term orbital radius, means that if this is the Earth and this is the satellite, okay, the orbital radius is from the center of the Earth to the center of the satellite. This is orbital radius. Okay, and the reason I'm saying this and clarifying it is because this is different than if I were to compare it to the surface of the Earth. This is called altitude. Okay, so the difference here, when we do R in FG equals G M1 M2 over R squared, that R is the distance between the centers. So if I give you altitude, you have to add the radius of the Earth to that. Okay, so there's a difference between orbital radius and altitude. So we're given orbital radius here, so that's good. So 4,500 kilogram Earth satellite has an orbital radius of that. What speed does it travel at? So I drew the picture over here, so I'm not going to do it again. But in this case, our FC is equal to FG. Okay. And then we're going to go mv squared over r, just like I did over there, equals gm m over r squared. Now, one of these masses is the satellite itself, so we can just cancel that out, and then we're left with the mass of the Earth. And so the speed, which we're trying to find, we're going to move this r over, r. Okay, that's going to cancel that r out, and it's going to cancel one of those r's out. So now we have v squared equals gme over r, and then square root that. So v equals the square root of gm over r. Now notice how the speed is only dependent on the radius. It's not actually dependent on the mass of the satellite at all. Okay, so it doesn't matter the mass of the satellite. The only thing that matters is how far away from the Earth it is. That's the only thing that will change its speed. Okay, so if we apply this, v equals 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by the orbital radius, 8.5 times 10 to the 7. And then we're going to square root that all. So 6.67 times 10 to the negative 11. And I'm hoping you guys are all using the like the EE button or the EXP button or the times 10 to the X button and not actually multiplying by 10 times 10 to the whatever. It just makes it way easier. So 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 8.5 times 10 to the 7. And then we're going to square root that, and we get a value of 2,166 meters per second. Okay, so this formula we have here, where it's v, come on, pen, v equals square root g m over r. Okay, this is to find the speed of a satellite. And it only depends on radius. Okay, the mass of the satellite itself does not matter. Okay, so it's a nice tidy little tidy little equation for us. So that is an introduction to satellites and applying gravity to satellites. One thing I'm going to say is notice how I'm not using mg anymore. Okay, so instead, like whenever I have FG, I'm not using mg anymore. Okay, it's fine if you're doing things on the surface of the Earth, but during this unit, you're never going to use mg. Okay, because the value of g is not 9.8 where the satellite is. Okay, when you're 8.5 times 10 to the 7 meters away from the center of the Earth, g is not 9.8. It's much less than that. Okay, and that's what we're going to talk about next lesson. We're going to talk about the value of g and how it changes depending on where you are in relation to the Earth. Any questions about this one?
On the formula.
Yeah.
Can you scroll down a little bit? Oh, yeah. Where is it? Yeah. What does the ME mean? ME.
Mass of the Earth.
Oh, mass. Okay. Got it. Yeah. Thank you.
Yeah. Yeah, I guess I should clarify that. Like, if it's not around the Earth, so a satellite around Mars, this mass will be the mass of the Mars. So this is the mass of the planet or moon, I guess. Right? If we put a satellite around the moon, you're not using the mass of the Earth, you're using the mass of the moon. Okay, because it depends on the value of gravity of the thing that it's orbiting around.
Is there going to be any opportunity to retake tests or replace any old test marks?
Okay. In terms of retaking tests, I'm going to say probably not. For some, I've had a couple people ask me how many are left. So we have circular motion, electrostatics, and electromagnetism left. And marks are due on Thursday. And so like Friday is a day off. And so like Thursday will be like your last, like your test will be due probably Wednesday night. So we'll actually probably not even do anything Thursday either. Unless we'll probably do your last test on the Thursday. So you'll do it like during class. So in terms of what's left, circular motion has a worksheet that I'm going to send home soonish, I think. Actually, it might be right now. Let me check that. It's like it's typically a quiz, but I give it as like a take-home assignment typically, but now it's just going to be an assignment because you guys are home. So that'll count for marks, and then the test. And then electrostatics has like, I think 5 quizzes or 4 quizzes or something like that. Like there's quite a few quizzes, which will count for marks, and then that test. And then electromagnetism, also the same thing. It has quizzes and tests. Now, in terms of, okay, this is a huge package. I won't be handing this out for a while yet. It'll be like it's kind of like the take-home assignment for circular motion is kind of like a review package that is for marks, let's say. In terms of final marks, it's like I'm willing to have conversations on the last day about marks. So if you think, like I should be at 95 and you made a couple mistakes on a test, like I would typically give a mock final that replaces your lowest test score and then a final exam as well to give you a better opportunity to bump your mark up. But because we don't have the time for that and I don't want to do that from home, I understand that, and I'm not going to be a jerk about it. I'll like if you say, if you're at 90 and you want 95, that might be a difficult conversation to have, but it's not out of the realm of possibilities, because like I know what I've seen all your transcripts. I know what kind of students you are. So it's not I can go based off of that. So yeah, that's kind of my story for now. Hopefully you're okay with that. But yeah, in terms of retests and all that, I don't feel very comfortable doing that. And I'm hoping we can get to the test, the electromagnetism test. But we'll have to see how far we get. Yeah, we'll definitely start electromagnetism, but we might not finish it. It's a pretty hefty unit. Electrostatics is as well. So yeah. And like in terms of difficulty, I would say like this unit and electrostatics are pretty similar. They might be they're pretty on par with momentum. So like however you did on the momentum test, that's roughly, might be a little bit easier than the momentum test. And then electromagnetism is a whole new ball game. Like if you get it, you get it and you'll do fine. But if you don't and you're struggling, then it's going to be very, very difficult. So yeah. Any other questions?
Do we have a finals test?
No final exam.
All right.
Okay. Any others? When is the assignment? I want to finish for sure lesson 4 before giving you the assignment. How much do we have left? And number 5. Okay, so we only really have 2 lessons left. I don't know if we're going to get both lessons done tomorrow. I think we only get 1 done tomorrow. Where's the gravitation stuff? Okay, so that's what you're working on now. Okay, that's nothing. So we might actually finish circular motion tomorrow. So I'll definitely hand it out tomorrow. Yeah, that's a good idea. I'll definitely hand it out tomorrow. And then you'll have weekend to work on review package or whatever. And then we'll do the test early next week. So yeah, so right now you can work on 5.3, and then we will probably do both lessons tomorrow at, I don't know what time yet. My wife works tomorrow, so I have all the kids, and I don't know how much I can teach with them upstairs, but we'll try to get through it all. So, okay, so just keep an eye out. It'll probably be 8:30 again. So let's stick to that. And yeah, that's it. Okay, so have a great day. And if you need anything, just message me. Okay.